Okay, so this handle assignment problem is not done completely yet. So we have to understand this now in more detail from the virtual point of view, which we briefly looked at it in the previous example. Let's just quickly summarize few of the key ideas and then we'll proceed further understanding the virtual keyword. And virtual keyword can be used both at the class level as well as at the methods level. So at both the level how it behaves differently we will understand. So we have already seen that it's legal to assign a derived class or a subclass handle to a base class handle, because derived class or a subclass is a special base class, which we have already seen. And what that means is whenever we assign a derived class handle to a base class handle, the functionality of the derived class object gets downcasted automatically. That is another way to say it. So we were saying that any overridden thing gets hidden, right? So the same thing I can say it as that the derived class object got downcasted automatically, because even when I had assigned a derived class object to a base class handle, when I try to access the overridden functionalities, I was not able to see the overridden functionalities. I was still accessing the property values that were assigned in the base class and the methods in a way that I had defined it in the base class, not in the derived class, right? So that is what we mean by saying downcast. Now, so now if in certain cases, if I want to prevent this from happening, that is, I have defined certain methods in the base class and I have extended that particular base class and I have implemented certain things in the derived class differently in the same overridden method. Now, even when I have assigned an derived class object handle to the base class handle, since the base class handle is now pointing to a derived class object, okay, and when I now access the common methods, I want the derived class functionality to be invoked instead of the base class functionality, right? If I want to prevent that automatic downcasting, all right, if I want to prevent that derived class functionality from getting hidden, what do I do? Right, so that is where this virtual keyword comes into picture. So if I add a virtual keyword to the methods in the base class, okay, then what happens is, irrespective of how you access a overridden method, right, irrespective meaning if you access it through the subclass or a derived class handle, obviously even in the without virtual keyword you will be able to access the functionality that is defined in the derived class. But now when you use the virtual keyword inside your base class, okay, virtual keyword for that particular method has to be used inside the base class, and when you extend that function or a task in your derived class and you define the functionality, and then when you create a derived class object and you assign that derived class object to the base class handle and you invoke a overridden method through base class handle, still the derived class functionality will get executed when you use a virtual method. Okay, that is what happens. But if you do not have the virtual method, then when you have non-virtual method, then you must use the class variable with a class type that has overridden method defined. That is what it is, right? So this is the foundation for the polymorphism. Okay, so we'll formally define it, but this is the foundation, that through the base class handle we want to access the functionality that is defined in the derived object through the overridden methods. This is the fundamental foundation for the polymorphism. Okay, let's look at an example of how this virtual works that will make it more clear. So I have one base packet class that I have defined. I have two integer variables, a equal to 1. I have initialized this variable a with the value of 1, initialized this variable b with the value of 2. I have declared two functions. One is of non-virtual type because you don't see a virtual qualifier over here, and a second function print b is qualified with the virtual keyword. And what are those functions doing? Each one of them is displaying one variable. So print a is displaying the value of a and print b is displaying the value of b. So now I have a derived object. So I am saying class my packet. I am extending the base packet. Okay, the base class I have extended, and I have overridden the properties. I am saying a equal to 3 and b equal to 4. Okay, there was 1 and 2 in the base and 3 and 4 in the extended class, and I am now overriding these two methods as well, the print a and print b. I am overriding and I am just displaying a and b. Okay, now let's say I create, so here I have not shown that code, but there is a P1. P1 is of the type base packet, which is new and constructed, an object of P1 is constructed, and there is a P2 which is object of the type my packet, okay, and that also is constructed. And let's call these methods and see what happens independently. So I call P1 dot print a, this is of the type base packet, so it's going to display 1, and I call P1 dot print b, it's going to display the value of 2. Okay, this is all, both of them are base class. Non-virtual, virtual doesn't matter. This only comes into play when we do the like the extension or the inheritance, right? And then I go to P2, then I call P2 dot print a, and then that guy displays the value of 3, and then I call print b, displays the value of 4. Anyway, I am accessing it with the derived class object type, derived class handle type. So no problem whether it was a virtual or non-virtual, I would have definitely gotten the value of 3 and 4 because I am accessing it with the object of that type. So I'm going to get the values of the properties of that type, no problem. I have overridden and I'm going to get the overridden values because the type is matching. But now comes an interesting point which we were trying to talk in the previous slides, that I am now doing and derived class object is assigned to a base class handle. Okay, so P1, I have a P1 which is of the type base packet, and I'm now assigning a derived class object which is of the type my packet to the P1. So I did this. Now I call P1.print a. Okay, so I call P1.print a. Now since I have a derived object, but what happens, since this method print a is of a non-virtual type, it is still going to, this particular functionality is going to get downcasted, or it is going to get hidden, and I will still see a value of 1. So I'll still see a value of 1 because this will not be visible because I'm trying to access it with a handle of this type. Whereas for when I do the print b, since this particular function has a qualifier called virtual, I will be able to see the value of 4, which is of the extended class functionality, right? So I'm able to see the extended or subclass functionality when even though I'm accessing it through the base class handle, when my method type is of the type virtual. So this is the fundamental way in which the virtual behaves. So using this virtual keyword, we can construct abstract classes. So before we construct, let's understand what is the concept of abstract class. So abstract class allows you to reuse the interface of a class. So what is the interface of class? Interface of class is the set of methods and properties that it is exposing publicly. Okay, we have seen it, right? So we can use like the concept of data hiding and encapsulation to protect what the external world sees this particular class or object as, right? So in the abstract class, what we do is we define set of these methods, okay, and those methods we want to reuse it at multiple places, okay. And why do we want to do it? We want a consistent implementation of multiple derived subclasses. So if we take an example, it will become clear. Let's say we have a subsystem, okay. In that subsystem we have USB, PCIe, your flash storage, UFS, you have the UART, you have I2C. Let's say we have multiple of these IPs which are part of those subsystem, and if we want to generate traffic to that particular type of a subsystem, and you want to do that, when you have your top level traffic generator, ideally you want your top level traffic generator to have a consistent interface to all these low level traffic generators, right? So that tomorrow, even if I had one more SPI block over here, right? So I should have a consistent way to start or stop the traffic on that particular block. So a top level traffic generator now can decide, pick and choose which IPs do I want to activate, and it should be able to have a consistent interface to invoke each of the low level traffic generators. So what I want a common interface. Let's say in this case, a very simple one. I can say init traffic, and I can pass some parameters to say how much traffic that particular traffic generator needs to generate. Then I'll say start traffic, it will start generating the traffic, and then I'll say stop traffic, and it will stop generating the traffic, right? So now this is the consistent interface that I want every of my low level traffic generators to implement. So how do I do that? I do it through the abstract class. So in abstract class, I'm just defining an interface. My interface is these three methods that I am providing, and then each of these low-level traffic generators will extend that particular abstract class and provide the implementation for each of those traffic. So in the init traffic, they will initialize their internal variables. Start traffic, of course, is going to behave very differently for USB, right? So for a USB, it is going to do like some data structure setup and do some DMAs and things like that. For PCIe, it might start generating some TLPs, and for flash storage, it's a different type of transaction. UART, we will see it in the future, that will start programming some of the bytes that needs to be transmitted, and so on and so forth. So each one of them is going to implement that interface differently but provide a common functionality. So when I say now USB traffic gen dot start traffic, I have a consistent interface, and I can say UFS traffic generator dot start traffic. So I can just say that and it will work. Internally, that particular traffic generator will take care of whatever needs to be done for that specific IP. But as a top level traffic generator, it doesn't have to worry about what the low level traffic generator is doing. Okay, so this is the common interface that I want to reuse across all the low level traffic generators. So I hope this idea of reusing interface is clear. We are used to idea of reusing a functionality the way we did it in the inheritance, right? So we added new functionality, or we took a particular function, overrided it, called super.thebase function, and then we added new functionality. That idea was very clear, where we were reusing functionality. That's very like a physical in some ways. But when we say reuse of an interface, sometimes it feels slightly, oh, how can just the definition be useful? But this is a way it is useful. You want to make sure that every low level traffic generator has a consistent interface, right? So that is where the abstract class comes into play, and it fulfills this requirement. And abstract class are declared with the virtual keyword. So we will look at that in the next slide. So okay, here we look at an definition of an abstract class. So an abstract class is defined with this virtual class base packet. So this is how you define. So any class that you call it as a virtual, okay, so this becomes an abstract class, and you never create an object instance of the virtual or the abstract class itself. Okay, why? Because abstract class is just providing you the interface. It's not doing anything per se. Got it, right? So that's why you don't really you don't have to create an object of the type abstract class. There is nothing that you can gain out of it. And within the abstract class, you generally define this pure virtual function. So we had seen virtual. This is a pure virtual. So what happens is the difference is when you define a virtual function in a base class, although you don't provide any implementation, or you can opt to provide some implementation, even if you're not providing any implementation, you still have to say end function or end task and provide the declaration for the virtual function or task. But when you use it with the pure, okay, you don't need to really provide any end function or end task. Okay, and what this means is that if I have declared an abstract class and I am declaring a pure virtual method in it, there must be a derived class, and it must rather than saying there must be a derived class, if there exists a derived class, then that must implement this particular pure virtual method. That's what it means. Okay, and in a way you can see that since this end task or end function is missing, it sort of shows that incompleteness. So if at all this abstract class gets extended, then this particular pure virtual methods must be implemented, otherwise an error will be flagged. Okay, and this pure keyword is not legal in non-virtual or non-abstract classes. Okay, so if this was not present, then you cannot use pure virtual. You can use virtual, but you cannot use pure virtual unless and until it's an abstract class. Is something that you want to remember. Okay, and pure virtual methods, they just create a placeholder, right, that imposes the requirement. Because as we talked about, even a virtual method can be implemented. It's just that it gets overridden, and the overridden functionality can be accessed through a base class handle holding a derived class object. But in the pure virtual function, you are not providing any implementation. Okay, you cannot do it. Got it, right? Since you cannot put end function or end task, you cannot provide any implementation to the pure virtual functions, right? And it must be implemented in the non-virtual class, whatever that derives this particular abstract class. You can do multiple level of inheritance with the virtual class itself, adding more and more interfaces. In those you still need to continue to either declare them as a pure virtual, or declare, if you declare them as a virtual, in the further extension you have to provide the end function or end task. But whenever you encounter the first hierarchy of a non-virtual class, okay, is a non-abstract class, then whatever the pure virtual methods that I have declared in the abstract class, you must provide the implementation. Okay, and most of the UVM based classes, like many of them are implemented as abstract classes with the virtual methods, because ultimately a methodology, you are giving some sort of guidelines and you want that consistent guideline to be implemented. So if I just say do this, nobody will do it, right? But when I provide an abstract class and I say these are my interface functions and you should extend this particular class in order to implement your functionality, thereby you are imposed a structure that you must implement, right? That is the idea of methodology. So most of the base classes will be internally using this concept. So we have put in all the foundation. Now let's understand the polymorphism. Okay, so what is polymorphism? Let's just define it out formally. And I mean, we have already looked at it in sort of an action, but we'll define it formally. And we'll look at one real use case to convince yourself that why it's a powerful concept. So polymorphism allows the use of a variable of a superclass type. Superclass meaning a base class, right? Formally, we are referring it as superclass type, to hold a subclass meaning extended or derived class objects, okay, and to reference the methods of those subclass directly from a superclass variable. It's very clear, right? So this we have already talked about it. That is what is a polymorphism. So polymorphism, you have a base class handle, you're assigning a derived or extended class object, and through that you are able to call the methods of derived class, and for that you remember we had used the virtual methods, right? So that is what we had done. But when you don't use a virtual, which is a non-virtual, what happens is the method code that you write, right, it kind of ties in, it gets fixed to the class object. Okay, so it only when you create a handle of that type, only then you can access the functionality. Whereas when you do the virtual method, what happens is that you are binding the functionality at runtime. Okay, so using the virtual, you are binding the functionality at runtime. You are not providing it immediately, right? And hence it becomes very powerful. Although you are binding it and you are able to access that with the base class handle. Now, why this base class handle accessibility becomes so important? Because I can assume there is a common functionality that needs to be done, and I don't know, like for example in the traffic generator we talked about, I want to build a high level traffic generator. I don't know how the low level traffic generator is going to behave. I can still build a high level traffic generator without knowing, or parallelly while the low level traffic generators are being built, I can still access it using my base class handle and be able to invoke the derived class functionality eventually during the runtime. So that is what makes it more powerful. So let's look at an example. So before we jump into this one, let's understand what is that I want to reuse. So there is a simple thing. What I want is, I want to send, let's say, some array. I have an array of packets, okay, and those could be of different types. So let's say if you take a Ethernet type of an example, there can be of different type of packets. There could be like a Ethernet type of a packet, there's a token packet, there's some GPS type of a packet. There are different types of packets that are available. I just want to send many of the packet types. So I want to write that code first. Okay, I don't have all the packet types. I don't know what are all the packet types, but I want to send them. So what I'm going to do, I'm going to create a base packet array, and I will just do, forget about this part of the code for now. I'll just do for each, and I'm going to iterate over that base packet array, and I will call send, and I am expecting this send to be implemented in each of those objects. Okay, so I have written this code, the line number 141 and line number 147 and 148. I have written this part of the code, and this is a reusable part. Okay, I don't care which type of a packet, but I want this functionality. Now, how do I make it work? Right, that is a question. So now, if I now look back, I have defined this virtual class, which is an abstract class, and I have declared one pure virtual function called send. And I have told everybody that you should implement this particular function, and then I am able to continue to build on the top of this base packet. Whatever the functionality that I want to do, I am able to build it with the base class handle type itself, because I don't know what are all the derived class handles will be, but I am continuing to build it, right? So I have provided that functionality. And then what happens, since I have provided it as virtual, now there is a guy who will extend it, and he will create a Ethernet packet which extends the base packet, and he will implement this particular function. He can still use virtual over here, okay, so that if somebody extends it further, he can again override it. So I am going to provide that functionality, and somebody will extend Ethernet packet and maybe create a token packet, and somebody might again independently extend a base packet and let's say create a GPS packet. Now all of those are extension of this base packet. All of these packets that I'm declaring are either extension of base packet or further extensions in that hierarchy. Okay, I am newing all of them, and I am filling them up in that particular array, because I can assign any derived class object to a base class handle. So I am able to assign it, and I am filling it up right in that particular array. And then this code that I have already written without even knowing what are all the different packet types that I am going to get, still my code will work. Got it, right? So in this way we are decoupling that I can still build some functionality using the base class handles, and it can work with the subsequent implementations of a structure that I have defined without having the availability of all those implementations, right? So this is where the polymorphism comes into play. That is the nature, that polymorphism, that a single thing manifests itself in a different ways, right? So this abstract class is one single thing which provides a common interface, right? Everything is same. When I extend it, right, it is behaving in different ways. That is the polymorphism, right? A single thing but behaving different phases, it is able to show it, right? But still I can always access everything through the base class handle. That is what is the polymorphism. Okay, so we had used this class scope resolution operator in the context of extern in the previous slides. We have already seen that. So we will look slightly deeper as to what are the other use cases for this scope resolution operator. The scope resolution operator is used to specify an identifier that is defined within the scope of a class. That's what is the formal definition for this scope resolution operator, and it need not only be used with the class. Actually, it can be used with a class or even the package names. If you want to access a variable that's present within the package, you can use a scope resolution operator. We'll see that in the package session. Even to access the items within the cover group also, you can use the scope resolution operator. So that we will see it in the cover group session. In this one, we'll keep it focused on class. So the main intention of the scope resolution operator is to make a particular identifier being uniquely identified, right? That is, if I have declared something within a task, and like let's say I have declared something within that the class level as well, and I want to now distinguish between them, I could say that particular class name colon that particular variable name to make the scope more clearer. So for that also you can use the scope resolution operator. But the main use cases that I have seen for the scope resolution operator are to access the public static members from outside the class hierarchy. This is the main use case. Like for example, if I have a class, this we have already seen this, but just to refresh it, we have a class, we have a static method called static task print. This can be accessed directly by using the class name and the scope resolution operator print. So one fundamental item that I want you guys to keep it in mind is that class is something that is dynamic, right? So unless you create an object of the type class, nothing really comes into existence. So whenever you use scope resolution operator with a class, it is always a good idea to access only the static items that are present within the class, okay? Because those are something those come into existence as soon as the class is declared. But whereas if you try to access the non-static properties using the scope resolution operator, there can be instances that you can face errors because it may not be existent, right? And then the LRM definition also in some of the cases is not very clear. So there can be different behavior when you try to access non-static type of properties using the scope resolution operator. So this is something that you need to watch out. And you can, so one is that you can access the static methods. The second is if you have a enum, and then if you want to access these enum constants, that's another popular use case for using the scope resolution operator. Here I can use the class name bin, which is a constant value that's present within this, like a named constant in this enumeration type that I have defined. So I can use it for this use case as well. And if you have any parameters, right, that are declared, those parameters can also be accessed using the scope resolution operator, because those are also static in nature. But by language feature, it allows access to even public and protected class members of a superclass from within the derived class using the resolution operator. But you have to be careful, as we discussed, that particular, if the properties are non-existent, then you could see some error cases over there. Okay, so we will look into the parameterized classes. So it's one of the advanced concepts within the class. So what the parameterized classes allows us to do is you can have a generic class, right, whose objects can be instantiated to have a different array sizes or data types. Okay, so this is the main functionality that is provided by the parameterized classes. And the reason to use the parameterized classes is it avoids writing a similar code for each size or a type. Okay, so this is something that will become clear once we look at an example. So let's look at an example over here, a very simple example wherein we will use the size parameterization. So class vector, remember we use this pound, and then we use the parenthesis, and in the parenthesis we can have a list of parameters separated by comma. You can have multiple parameters that are separated by comma, and then you use, once you have declared a set of parameters, those parameters can be used inside your code for declaring other variables. Okay, or it can be used within the properties as well to pass the arguments. It can be used for whatever the processing that you are implementing. You can use these parameters, right? So here we are declaring a bit vector which is of the size that we have created as a parameter. So size -1 colon 0, we are declaring a bit vector of the parameter size, right? So now once we do this, then what we need to do is we need to now pass a particular value to this parameter, and then only we actually create a real data type. That is, if a combination of your generic class, so generic class is a vector. Okay, so the vector is a generic class, and we have anyway defined a default value for the parameter. So along with the actual parameter, so the generic class along with the actual parameter values, right? So here a parameter value of a 10 plus the generic class vector, it actually becomes a data type called v10. Okay, so if a generic class is not a type, only the concrete specialization represents a type. So this is another important point, that now if I try to, like for example here, right, so if I try to use the scope resolution operator and try to access vector :a, and this is just a generic class, okay, assuming that we are not passing any default value over here, then this would not be a legal way to access it. Okay, because it's not a specific type anymore. Okay, whenever we pass the actual parameter values, then only it becomes a real data type, and whenever we pass a specific value, it becomes a new data type. Okay, so now if I create a vector of 10 and a vector of 2, although we are creating it from the same generic class, because the specialization is different, those two are not same data types. They are not same data types. Those are two different data types. So this is one important point that you need to keep it in mind. So even though we are using the same generic class, because of the different parameter values, the different data types themselves get created. And if you want to create variables of different, like multiple variables of a particular specialization, you can use type def. So I can say type def vector hash 4, I will say v4. Now I have created a data type, not a variable. Okay, so here this v10 and v2 are variables, whereas v4 is a data type. So now I will have to again use v4 and then pass in the name of the variables that I want. So then I can create multiple variables of this type anywhere, right? And those will be again of the same type. And the another concept associated with the parameterized is it not only that you can parameterize in terms of size, you can parameterize in terms of data type as well. Okay, so here I have created a stack, right? Stack is something where it's like a last in first out type of a data structure, right? So I have created a stack and I want this stack to be of type like whatever it should be capable of storing any data type that I have, right? So I have parameterized the type itself. So when you say type t equal to, then it represents a data type parameterization, and I'm passing a default value of int. Then I am declaring a dynamic array, and then I am declaring the push and pop task, which I can later implement. So now when I declare a stack, which is a generic, and when I say whatever is, now here what happens is becomes a stack of ints because I have the default parameter value assigned with the int. Okay, now I can also say stack of, and then here I am passing bit 1:10. So now this stack will be implemented with this data type. I can also say stack found real. Okay, so now I am implementing a stack is a generic class with the specialization of real. Okay, that I can do. And the parameterized classes can also participate in the inheritance. So for example, I can have a base class. So I am saying class C, it's parameterized with a type t equal to, and then I have put the default value as bit and end class. Now I can extend this parameterized class C with a D. So I'm saying class D1, and then this D1 itself is again parameterized separately with a type type P, which the default value of real, and extends C, and the default value of C will be specialized with the bit. And also I can do like a class D2, which is parameterized again with a type P, default type of being real, extends class C of integer type, right? So I can create a specialization of integer type and extend it. So parameterized class can be extended from another parameterized class. And these two concepts, the parameterized classes combined with the abstract classes, right, is what forms the primary concept in building the UVM base class libraries. So this is what something that we will see as we go further in the methodology section. We will see. So these type of generalization help build class libraries. So that's where these type of concepts find a lot of application. So most of these advanced concepts, they find application either in a very complex verification or in building the class libraries. So we have seen that the classes are dynamic objects, and then if you are coming from a C type of a programming background, you would have seen that there is a concept of malloc and free. Okay, so that type of a concept doesn't exist in the SystemVerilog, and this is done because of the multi-threaded nature, right? As we have discussed multiple times, the HVLs or HDLs, the primary thing that distinguishes them from the procedural programming languages is their parallelism. So by default, when you look at a Verilog or a SystemVerilog, you try to look for the parallelism that exists. So because of the multi-threaded nature, it becomes difficult to figure out when the usage is completed. Like for example, I created an object, okay, and when I created this my class object, and I have forked off 2 tasks, and tasks can be time consuming. Now where should I deallocate this particular object, right? There is no clear sense. If I have this type of a structure, I don't know when is this going to end, and all that. Even if I can figure it out, it becomes very complicated in the bigger scheme of things. So SystemVerilog, what it does is it automatically allocates and deallocates the memory on need. Okay, and what is the responsibility of user is in order to make it run effectively, you need to make sure that if you have any big arrays that you are declaring, right, then you make sure that you assign those arrays to empty entry, like for example, if you are using a queue or something, then you can call the delete to clear them off, right? After you have done the usage, you can clear them off, and object handles, after you are done usage, you can assign null, right? And for objects to be deallocated, as we have seen in previously also, in the context of that driver and generator interaction analogy, we have seen that it gets deallocated only after all the references are assigned to null. Okay, so for example, here if I take this example, so I am saying object 1 equal to object. Okay, so I'm assigning this handle. Then I am saying object equal to null. So what happened is, when I said new, an object got constructed and the pointer to that is present in this handle obj. Now that pointer is also present in obj1. So two handles are pointing to the same object. So now one of the object assigned or dereferenced that particular object, but still obj1 is holding the pointer to the object that we have constructed. So that particular object area that we have allocated, storage memory, will not get deallocated. Only when I say obj1 equal to null, that all the references to that particular object, there's no handle that's pointing to that particular object, then only the deallocation takes place. And also many of the simulators, this is again one of the advanced feature, they provide profiling. Okay, so in the profiling, what they will tell you is, they will tell you how much memory, how much compute resource a particular part of your code is consuming. Now you can often look at that and figure out if there is a scope for optimization. So this should be done to keep your, even though you are writing a verification code, you still want it to run efficiently. So we have looked at the type def for creating user defined types. Let's see, this has one special use case in terms of the class. Let's look at that. So let's say if I have class C1 and then I have another class C2 and they are instancing each other. So class C1 is instancing C2, now C2 is instancing C1. So this way we have a sort of a cyclic dependency, right? So now when I have this case, assume that this line 209 is not present, then when we try to, the compiler tries to compile the C1, it won't find the definition of C2, and because of that it will throw a compile error. So in such cases, what you do is you use the type def and you say type def class C2, and here the C2 is declared to be of the type class. This is called as a forward declaration. So it's an important concept. So it is called as forward declaration, and this tells the compiler that the actual definition of this class will follow. And if you don't provide the definition, then it will flag the error at the end if it doesn't find anything. But this tells the compiler that it will find it later and it will continue. So now when I say C2 of C, it won't flag an error and will continue. So you can use the type def of the class to do the forward declaration in order to solve the cyclic dependency problem. Okay, so we'll look at interface class. So interface class is, as we discussed at the beginning, it's a super advanced concept. We are not going to go into very details of it. We'll just get a flavor of it as to what it does at a very high level. Because if we want to go and cover all the details, it's a session by itself, and it'll take few hours. But it's not the time constraint; it's the usefulness, right? So the main usefulness of the interface classes comes in like the library or the verification methodology development. In the regular test bench development, the usage is very limited. Unless it's a highly very super complex area, the interface classes won't be that useful. So it's mainly, but it's predominantly used in the like library development. Even within the UVM, these concepts are utilized. And before we get into this interface classes, first thing I want to tell you is, don't get confused between the SystemVerilog interface, right? The signal level interface that we saw versus the signal level in the SystemVerilog interface class. These are two different concepts. They are not same. Okay, and it will look similar to abstract class, but when we see when you explore the further details, what happens is, like when we had to pass the subclass, when we had to pass the different hierarchies, right? Like we had a subclass, we wanted to assign it to base class handle and then bring it back to a subclass handle. We had to jump through those $cast and that concepts we had to understand, right? So those baggages will not be there with the interface class. So that makes it slightly easier. Now the basic idea of interface class is that you have some common functionality that a particular class needs, and which needs to be implemented by multiple classes, and it will take that and put it together and implement a final functionality. That is what it wants to do. Okay, so that is where the concept of interface class will come in to be handy. Okay, I think let's look at one or two examples, small examples as to how this particular statement manifests. Okay, so there are four different use cases for the interface class. So first one is called observer or a subscriber type of a use case. So what happens here is, so we have a monitor and we want to feed the output of the monitor to multiple other modules. So I want to feed it to scoreboard, checker, I could have a coverage collector. So I want to feed it to multiple blocks. Now in the FIFO test bench, if you remember, we had push monitor and pop monitor from where we were feeding transactions to the scoreboard, right? And let's say we had a coverage collector over there, then we had to feed it to coverage collector as well. So now if I want to feed these transactions to multiple components, I have to create separate instances of mailbox. Now let's say if I want to design monitor such that it can handle any number of connections, any number of guys could get connected to monitor to take transactions to do different activities. One could be a performance monitor, another could be coverage collector, you could have scoreboard. So there could be different components that want to get connected to monitor, right? And how many of them get connected may not be known upfront. So that's first problem. Second problem, even if I know, let's say I want to connect three components, if I create three instances of mailbox and start putting in all three of them, and then one of the component finally doesn't get connected, let's say coverage collector doesn't get connected because we have disabled functional coverage, then what happens from that mailbox? It will just simply keep piling up, it might become full and give error. So these are some of the real problems that prevent building a very configurable test bench. So in UVM, we will see we have this concept of analysis port. The symbol of diamond is actually analysis port in UVM. And that gets, so the concept of this analysis port allows us to do zero to many connections. So you can have zero number of connections, will still work. It can have many number of connections and it will still work, right? And those connections can be dynamically scaled up or scaled down, and that will also work. So that type of a pattern is implemented through interface classes in UVM. Okay, so now what is happening if you look at it, if we go back to our definition of the interface classes, that the problem that we were trying to solve, a monitor is detecting a transaction, and after it has detected transaction, these all things I want it to happen on that particular transaction. I want it to be scoreboarded, I want it to be checked for this thing, and let's say I want it to be covered. So these are all the three different items that I want, three different processing that I want on the transaction that I have gotten in the monitor. Now what will happen is I cannot put all this functionality within this monitor, right? So now I have to spread this out, correct? That's what we were talking about. So there is a functionality, there is a common functionality that is required, but it's not implemented in the same component. It is spread out in the different components, right? So whenever a transaction is detected, I want scoreboard to do some function. That functionality is, in a way, if you think about it, it's the job of a monitor, because this guy has detected a particular transaction and whatever needs to happen on that particular transaction has to be done. But I am spreading out that common functionality in different components right now. And how do I connect this? That was the problem that the interface class is trying to solve. The second problem that the interface class is trying to solve is called something called multiple inheritance. So what this multiple inheritance means is, let's say I have this class A, I have derived it in B, I have derived the class in C. This A doesn't really matter, I'm just showing it as a picture to make something complete. But what matters here is there is this class D that wants to now derive both B and C. Okay, so it wants to derive from both B and C. So that is a multiple inheritance. So when I do my regular inheritance with the extends keyword, I can only extend one class. I can't put a comma separated list over here. That can be done in Python, for example, but not in the SystemVerilog. SystemVerilog, you can currently extend only one class. So if you want to implement something like this, then one of the solution is you use the interface class, and when you use an interface class, the way you kind of implement or extend the interface class is using this implements keyword. So you say this particular class is going to implement these two interface classes, right? So now in this way I can do multiple inheritance, and the multiple inheritance is useful in data serialization, and then there is a concept called object clocking. We will look at one of these examples. And then there is a BU specific policy implementation. BU specific means a business unit. So what happens is that you implement some libraries, and in the companies there can be different groups, and they want to implement certain policies saying that when this particular class gets implemented, we must do this. So if you have a AXI interface, AXI functional coverage model must be integrated and included in that, right? Or if I am doing some sort of a performance monitor, then this particular logging has to be followed in certain format. So I have certain policies that I want the teams to implement, then those things can be done through the interface classes. Okay, that is what is the BU specific policy implementation. So yeah, so these are the some of the application for the interface classes. Let's look at one example of like how does this object clocking works. So here is an example. So the object clocking problem is something like this. So what happens is that when we like provide the clock separately, same clock is being provided separately to different blocks through different interfaces in the test bench components I'm talking about. There are again some cases where there are issues with the races that come in. Okay, to prevent that, what is done is that there is one global clock generator block that is defined, and that clock generator block defines event called like a talk, and this can be now provided to all the components, and you can now distribute the events to all your test bench components so that they execute in a specific order. Okay, so that is what is done. This is done in a very advanced type of scenarios. I'm just showing you for the sake of example. So the way you do is you first define an interface class. So the way we had defined virtual class, now you define a interface class called clockable, and similar to the abstract class, you define this pure virtual function, because this must be implemented. That is why it's called as pure virtual function over here. And then this clock center is the global class that's implementing all the, I mean that's correct, building on the common functionality that is implemented by multiple classes that are extending the interface class. Okay, so this is the central guy. Now let's say this what I'm showing it on the right hand side, there could be many such classes that will be extending some UVM component and implementing this particular interface class. Okay, so what does this mean when I say interface class? They will get this particular, whenever they say implements this particular interface class, whatever the pure virtual functions that I have defined over here become a part of this particular class who is implementing it. So now this talk becomes a part of the interface timeout monitor, and here now I can look at, I can do the processing, I can increment some counters, and if that counter is greater than timeout, I'm looking at idle. So this is one of the technique that's used in the test bench. So you look at idle, and if the interfaces remain idle for certain duration of time, then it is an indication that the stimulus has completed and something is hung, right? Because what happens towards the end of the test is after everything is done, either the test finishes, right? It has to finish, and if the test is not finishing, then there must be some activity on the interfaces. If there's no activity on the interface, test has not finished, then it means like an, you know, the idle duration is there for a very long time, which means somewhere something is hung and test is not making a forward progress. So in those cases, what will happen is we will have an idle monitor that will check that interface has become idle. We keep incrementing the counter, and when the counter crosses that particular timeout value, then we are saying that this particular is an error. UVM fatal will terminate the simulation. Okay, and in this talk we are emitting the count at every clock tick. Okay, so that is what we are trying to do with the help of this particular interface class. Okay, now what we do over here is that in the central place we have created one struct struct, and we have declared this clockable interface class object and the name, so that everyone can be registered to this particular clocking center. And then we have declared of this struct type, we have created one queue out of it. And then whenever any of these classes that are implementing the interface class, to make sure that this function gets called, what they need to do is they need to register it to the clockable center. So they are saying clockable center get instance. This is something that's provided by the concepts that are used in the UVM. So we will look into it more detail. For now, just understand that we get the singleton instance of this clockable center, and we register this guy, right? Register this particular instance. So that goes in and sits into this particular dynamic array, right? And by over here, right? So when I call this register clockable and I am passing this object and the name, so it gets into this particular dynamic array. Okay, once it gets into this dynamic array, then what I am doing here is in the run phase, don't worry about this, focus on this. So at forever at clock means on both the pos edge and neg edge, for each of these clockable objects that I have been registered, I am calling m clockable of I. Okay, then that particular whatever the object that is registered dot object dot talk. Okay, so what happened? If multiple guys like this had registered, all their object instances had gone into this particular queue, and for each one of them now talk gets distributed. Is similar to register, you can have unregister as well, and they can remove it. And as many people who wants to receive talk can register over here. And if none of them are registered, no problem, right? This loop will not execute because this particular queue will remain empty. Got it, right? So this way what happens is that we are able to do one-to-many type of a event distribution. Okay, this is the concept of the interface classes. So in summary, you kind of declare it like an abstract class, but instead of extend, you say implements, and when you say implements, this functionality becomes a part of the class that is saying implement, and then you have one central entity wherein you hold all the objects. So here if you look at it, we are not doing any dollar casting, right? When I access this particular object and talk, it went to call this derived objects function. We don't have to do casting, right? Although we had created here the base interface constructs handle in this particular struct, and I am registering the extended class handle. In a way, I should not call extended, but the implementer class handle, I am still able to access the functionality that is present within this particular class who is implementing without having to do any dollar casting. Okay, that's the one point that we had discussed before. So this is how the concept of interface classes works. Is one of the example that I am showing. There are various ways to utilize this and build more flexible solutions that are typically used in the verification libraries and the methodology implementation. Okay, so this concludes the session on class, and we started off with why do we need object-oriented programming. We could see that it provides it enables building good softwares, and we understood that a good software needs to have high cohesion and low coupling. That is, all related things should stay together, and unrelated functionalities should be loosely coupled. Without knowing the details of the other class, you should be able to access the functionalities. And then how the object-oriented programming promotes that through its concepts like abstraction, then the data hiding, encapsulation, inheritance, and then the polymorphism, right? So we looked at each of those areas. So we understood the abstraction enables us to group all the related functionalities together, the properties and the members, and then with only certain interface functions we can access the functionality of class. Inheritance allows us to do the functional reuse, right? So the functional reuse could be in terms of two things. Anytime we say word reuse, right, we are building on top of something. So in inheritance, we could add new functionality by adding new properties and functions, or take existing tasks and functions and add more functionality to it. And then we looked at how the keyword this and super are used over there, and how we use the super in case of inheritance where we wanted to extend the functionality of a particular task or function. Then we looked at how the assignment between the class data types behaves when we have the inheritance, right? And we saw that if we assign a derived object to an object, derived object to a base class handle, and we try to access the derived class functionality, then it won't be visible, it will be hidden or it gets downcasted. And in order to solve that type of a problem, we looked at the concept of virtual functions, right? When we did the virtual function in the base class, when we implemented it, even the derived object overridden functionality could be accessed with the base class handle, and that formed the foundation for the polymorphism. We looked at the abstract classes, which are virtual classes with the pure virtual functions, and using that we were able to use the same superclass handle to access the overridden functionality in the subclasses. And primarily we did the interface reuse, right? That set of common functions, if you remember that generator example, right, where we wanted start, stop, or the init type of a common interface for all different generators to be available so that the top level generator can use. So that was one of the use cases that we saw for the polymorphism. And then we looked at the mainly the concept of parameterized classes. So how the parameterization helps to define customize it for the size of arrays or for the different data type. We looked at that, and then we jumped into this super advanced concept of interface classes, wherein how to distribute the common functionality among different implementations and yet stitch them together in a common implementer. So we looked at that. So overall, I think this concludes the object-oriented programming using SystemVerilog. Is one of the foundational new programming paradigm that you have learned, and this will be used everywhere now on. Okay, this will be relevant even when we do the constraints. This will be relevant when we do the coverage, and the concepts of inheritance, polymorphism are extremely important when you go to UVM. Okay, when you go to UVM, you don't really need to know the interface class. The reason why I explained you is to just to have a sense of exposure, because interface class will be hidden. You will just be implementing the functionalities that is defined in the UVM. So you just need to know that that type of pattern has been used or the parameterized class has been used. You yourself may not really build those things, but you need to know that those things exist and they are used as a foundation to build the UVM based class libraries. But the concept of class will be used now on in every area, and so you make sure that you get the clarity in this foundational concepts. Okay, so thank you for listening.